Welcome back for day 11 of our Explainer series. Today, we're breaking down a massive architectural shift in how we build AI. We're looking at the move from single-agent setups to multi-agent systems. There's a really common misconception when we start building AI applications. We tend to think that simply adding more tools and more complex prompts to a single agent automatically makes it smarter. But in reality, it usually just creates a massive multitasking bottleneck. So by the end of this explainer, you're going to understand exactly why a team of specialized agents actually works far better than trying to build one omnipotent super agent. Let's build some intuition for this. Think of a highly capable solo developer. They're writing the back end, designing the front end, managing the deployment, the whole shebang. It's one incredibly smart unit juggling absolutely everything. That is your classic single agent system. But as we all know, even the best multitaskers eventually hit a wall. Now imagine a coordinated team instead. You've got a dedicated database architect, a front-end specialist, and a DevOps lead. Everything runs in parallel. You get fewer mistakes and zero burnout. That right there is the core idea behind a multi-agent system. Instead of forcing one agent to do everything, a group of specialized agents work together to tackle complex tasks. Now, to be fair, single agents are absolutely excellent for focused, linear workflows. They're autonomous, they're predictable, and they are cheap to deploy. If you're building a simple FAQ bot, a single agent is perfect. It hits the nail on the head. But ask that exact same bot to screen incoming resumes, schedule 3 rounds of interviews, and then negotiate salaries, the system becomes incredibly brittle. A solo agent simply struggles to adapt when faced with those kinds of layered, unpredictable workflows. So let's formalize this a bit. A multi-agent system, or MAS, is essentially a network of AI agents working collaboratively. And the key technical distinction here is that these agents don't just act independently in a vacuum. They actively model each other's goals, they share memory, and they cooperate. They're highly aware of their environment, and crucially, that environment includes all the other agents in the network. So how exactly do they do this under the hood? Well, it all comes down to communication protocols. First off, agents share real-time sensor data. Next, they exchange episodic memory, which is just sequences of past actions and their outcomes. When one agent learns a successful strategy, it actually distributes that learned policy across the network. This prevents the whole system from getting stuck in repetitive learning loops. Think about it. If one agent figures out how to parse a really difficult data format, the others don't have to relearn it from scratch. This shared state guarantees some pretty incredible fault tolerance. When designing these systems, engineers actually have a few architectural choices. You could build a centralized network where a primary unit holds all the global knowledge. That's easy to manage, but it's risky if that center node fails. Then you have decentralized networks, which let agents share information only with their local neighbors, making the whole setup highly robust. You also see hierarchical structures, kind of like a corporate org chart, or even what we call holonic coalitions. That's where autonomous agents temporarily merge together to tackle a massive task, and then gracefully disband once the job is actually done. What's genuinely fascinating is that these architectures lead to emergent behaviors that often mimic nature. Take flocking algorithms, for instance. They keep software agents synchronized, maintaining separation and alignment just like a flock of birds in flight. Then there's swarming, which allows massive numbers of agents to self-organize. Because instead of an engineer manually programming thousands of individual if-then rules for every single agent, which honestly sounds like a complete nightmare, we apply swarming heuristics to reliably manage the collective. So what's the architect's heuristic here? How do you choose? If we break down the scenarios, it really comes down to workflow complexity. You're going to want to choose a single agent system when the task is linear, processed sequentially, and confined to a single tool. It's fast, it's lightweight. But you should shift to a multi-agent system when your process spans different platforms, when it demands distinct specialist roles, or requires parallel execution. If you need modular scalable control, multi-agent is definitely the clear path. And we are seeing these multi-agent systems in high-stakes production environments right now. Over in smart cities, decentralized AI agents manage entire traffic light networks, adapting in real time to ease congestion. In Amazon's warehouses, massive fleets of collaborative robots coordinate shelf movement without colliding into each other. In healthcare, distinct agents are managing ER triage, matching patient flow to available rooms entirely in parallel. Practitioners leverage the setup because real-world environments demand absolute resilience, not just speed. To wrap things up, a multi-agent system isn't just about doing more things at once. It's really about specialization, distributed problem-solving, and resilience. So your one key takeaway for today is this. When specialized agents collaborate, share memory, and learn together, the intelligence doesn't just add up, it compounds.